Deep in the Antarctic ice, a single subatomic particle crashes into a detector. It is a ghost, completely invisible to the human eye. It's called a neutrino. It traveled for over 4 billion years, passing straight through stars, planets, and galaxies without hitting a thing. But where did it come from? It didn't come from a normal star or even from a massive supernova burst. It was fired from a cosmic cannon. A supermassive black hole shooting a relativistic jet of pure energy straight at Earth. Welcome to the terrifying reality of Blazars and Quasars, the universe's most powerful engines and its most dangerous death rays. To understand the scale, if you shrink the entire Milky Way galaxy down to the size of a massive bustling city, a quasar would be a tiny glowing grain of sand in the center. Yet it outshines the entire city by a factor of 1,000. How is this kind of power even possible? Let's travel back in time, deep into the cosmic void, to see the monster up close. At the exact center of almost every large galaxy in the universe, including our own, sits a supermassive black hole. Most of the time, they are sleeping giants. Our own black hole, Sagittarius A star, is currently on a very strict, quiet diet. But when a black hole is actively feeding, pulling in massive amounts of stray gas and dust, the monster wakes up. The material doesn't just fall straight in, it spirals around at immense speeds, forming a massive glowing whirlpool called an accretion disk. Extreme friction and gravity heat this disk to millions of degrees, causing it to emit brilliant, blinding radiation across the cosmos. This is an active galactic nucleus, or AGN. It is the central engine that powers the brightest objects in the universe. But the glowing disk is just the beginning. The danger comes from what happens next, at the thick poles of the black hole. According to astrophysical models, the black hole's rotation twists its magnetic field lines into incredibly tight coils at both the north and south poles. These twisting magnetic tornadoes act like the ultimate particle accelerators. They grab infalling matter before it crosses the event horizon and powerfully launch it outward into space as twin beams of ultra-hot plasma. This is the infamous relativistic jet. These plasma beams are expelled with such immense force that they travel at up to 99.9% the speed of light. If you tried to measure that speed, your radar gun would simply break. It's the absolute cosmic speed limit, harnessed by gravity. These jets don't just stay near the black hole. They extend far beyond the boundaries of their own host galaxies. Observations from NASA's Chandra X-ray Observatory have detected jets stretching over 300,000 light-years into the cosmic void. To put that in perspective, that is a single beam of energy 3 times wider than our entire Milky Way galaxy. Even with the largest ruler imaginable, trying to measure a relativistic jet is a humbling experience for any cosmic explorer. For decades, scientists had no idea these monsters existed. Back in 1963, astronomers were confused by mysterious, bright dots in the sky. They looked exactly like normal stars, so they called them quasi-stellar radio sources, or quasars for short. But one object, 3C273, changed everything. Dutch astronomer Martin Schmidt realized this star was actually moving away from us at massive speeds, placing it 2.4 billion light-years away. To appear that bright from such an extreme distance, 3C273 had to be emitting the continuous energy of 4 trillion suns. He had just discovered the first quasar. Not a star at all, but a supermassive black hole, actively feeding and illuminating the early universe. So, if a quasar is just a glowing accretion disk and a massive jet, what exactly turns this object into an extreme blazar? To understand a blazar, you don't need to learn any new physics. You just need a change of perspective. Imagine holding a flashlight in the dark. If you look at the flashlight from the side, you can clearly see the beam of light cutting through the dust, but it doesn't blind you. But if you turn that exact same flashlight and point it directly into your own eyes, the light suddenly becomes overwhelmingly, painfully bright. This is exactly what happens with an active galactic nucleus. When we view the glowing accretion disk and the jets from a side angle, astronomers call it a quasar. It is incredibly energetic and bright, but the main beams of radiation are pointing safely away from Earth. But what happens if that galaxy is tilted in space? What if that massive, relativistic jet of plasma is aimed directly down the barrel at us? Due to extreme physics called relativistic beaming, or Doppler boosting, the light moving toward us is compressed and exponentially amplified. It appears up to 10,000 times brighter than it actually is. When you are staring directly into this cosmic beam, it is called a blazar, which brings us back to the ghost particle in the ice. In 2017, the IceCube Observatory in Antarctica detected a high-energy neutrino. By tracing its trajectory back through the cosmos, scientists pinpointed its exact origin, a blazar named TXS 0506 plus 056. This supermassive black hole is located 4 billion light-years away, yet its jet was perfectly aligned to shoot a particle straight into our planet. It was a monumental discovery. The first time in human history, we traced a high-energy particle back to a specific active cosmic engine. Think about the sheer precision. A perfectly aligned cosmic beam firing across billions of years of space, hitting a target the size of a grain of sand. We are constantly in the crosshairs of these distant giants. Thankfully, at such extreme distances, the radiation diffuses and is completely harmless when it arrives. But that raises a terrifying question. What if a blazar was located much, much closer to home? What if our own galaxy suddenly turned its beam on us? To truly grasp the terrifying power of these cosmic engines, we have to look at the numbers. Let's start with something familiar. Our Sun. Our Sun is a massive nuclear furnace, but compared to the universe's true giants, it's just a tiny spark in the dark. When one of these massive stars reaches the end of its life cycle, it undergoes a supernova, a brilliant cosmic burst of energy. For a few brief weeks, that single stellar burst can outshine the combined light of its entire host galaxy. It is nature's ultimate fireworks display. But a quasar can outshine a supernova by a factor of thousands. And unlike a brief burst, it does so continuously for millions of years. If we do the math to calculate the exact energy output, the numbers stop making sense to the human brain. A powerful blazar, with its relativistic jet pointed straight at us, can emit more energy in a single second than our Sun will produce in 10 million years of continuous shining. Just 1 second versus 10 million years. It is a level of power that challenges our understanding of physics. In fact, there is a physical limit to how bright an object can be. It's called the Eddington limit. If a black hole eats matter too quickly, the intense radiation physically pushes the incoming gas away, cutting off its own food supply. So, a quasar is a perfect cosmic balancing act between gravity pulling matter in and radiation pushing it out. It is the most efficient engine in nature, converting mass into pure energy with flawless, terrifying precision. And the excess energy that escapes this balancing act, it gets channeled into those extreme relativistic jets. These jets don't just look impressive, they act as cosmic sculptors, actively shaping the destiny of the entire universe. For a long time, astronomers wondered why some galaxies suddenly stop making new stars. A healthy galaxy is filled with glowing blue gas, giving birth to millions of stars. But then, the monster in the center wakes up. The supermassive black hole begins to feed, igniting into a brilliantly bright quasar. The intense radiation and the massive relativistic jets act like a cosmic hurricane. They forcefully blow all the cold, star-forming gas out of the galaxy. Without that gas, no new stars can be born. The galaxy ages. The blue stars die out, leaving only older, cooler red stars. The galaxy becomes red and dead. In astrophysics, this dramatic process is called quenching. The central black hole actively shuts down the life cycle of its own host galaxy. For years, this was just a solid theory. But then, humanity launched its greatest eye into the cosmos, the James Webb Space Telescope. By looking deep into the infrared spectrum, JWST peered back in time to the cosmic dawn, just a few 100 million years after the Big Bang. And what it found completely shattered our models of galaxy evolution. It found ancient quasars that were fully formed and feeding at impossible rates. JWST captured direct evidence of these supermassive black holes actively blowing away the star-forming gas of their host galaxies. The data showed that these quasar winds were pushing out thousands of solar masses worth of material every single year. Think of the black hole not just as a destroyer, but as a cosmic thermostat. It regulates the temperature and growth of the entire galaxy. If the galaxy grows too fast, the quasar ignites and pushes the gas away, cooling things down. It is a delicate, violent equilibrium. This means that without quasars, the universe would look completely different today. Galaxies would be overwhelmingly massive and chaotic. A single black hole, hidden deep in the center, has the power to dictate the fate of billions of stars. It is the master regulator of the cosmos. But remember, our own Milky Way galaxy has a supermassive black hole too, and it is currently asleep. What happens when it wakes up? Right now, sitting 26,000 light-years away in the exact center of our Milky Way is Sagittarius A star. It is a supermassive black hole with the mass of 4 million suns. But right now, it is starving. It is a sleeping giant. But in about 4.5 billion years, our galaxy will collide with the Andromeda galaxy, and everything will change. This immense collision will flood the galactic center with fresh gas and dust. Sagittarius A star will wake up, forming a blinding accretion disk. It will become an active galactic nucleus, a quasar, and its magnetic poles will launch twin relativistic jets into space. Now for the terrifying part. What if the chaotic physics of the galaxy merger cause one of those jets to point directly at our solar system? Because the beam travels at near the speed of light, we wouldn't see it coming. Suddenly, a second blindingly blue sun would appear in our night sky. At a distance of 26,000 light-years, the beam wouldn't instantly vaporize us, but it would unleash a relentless wave of extreme X-rays and gamma rays. This profound energy would trigger atmospheric stripping. It would completely obliterate the ozone layer within months. Without the ozone layer, the surface of our planet would be bathed in lethal levels of ultraviolet radiation from our own sun, fundamentally altering the biosphere. Even from halfway across the galaxy, the sheer concentrated power of a Blazar jet is enough to profoundly disrupt planetary ecosystems. It reminds us that the universe is not just a collection of quiet stars. It is an active, dynamic arena filled with engines of unimaginable power. But take a deep breath. This is just a thought experiment. The chances of this perfectly aligning with Earth in the distant future are incredibly slim. For now, and for billions of years to come, our galactic center remains quiet. We are safe to simply look up and marvel at the stars. But those ghost particles, the neutrinos from distant blazars, they are still passing through you right now. A silent reminder of the monsters in the dark. So, we know that quasars and blazars are the most powerful engines in the universe. But a profound question remains. Do they last forever? The answer is no. Eventually, over billions of years, a supermassive black hole will simply run out of gas and dust to eat. The majestic relativistic jets will power down. The galaxy will grow dark and quiet. But the black hole itself, it is not completely immortal either. Enter Stephen Hawking. He proposed that at the microscopic quantum level, the edge of a black hole is actually boiling with activity. Occasionally, a pair of these particles forms exactly on the boundary. One falls into the black hole, while the other escapes into space. This escaping particle is known as Hawking radiation. It means that, incredibly slowly, the black hole is leaking energy and losing mass. Over an unimaginably long time frame, trillions of years, even the most massive monsters that once powered quasars will slowly evaporate. But this creates a massive problem in physics. It is called the black hole information paradox. In quantum mechanics, information can never be truly destroyed. The exact physical state of every atom must be preserved somewhere in the universe. But when a star or a planet is swallowed by a quasar and falls past the event horizon, that information is locked away forever. And if the black hole eventually evaporates completely through Hawking radiation, where does all that stored information go? Is it deleted? If the information is deleted, it breaks the core laws of physics. But if it escapes, how does it get out of a black hole? This paradox remains one of the greatest unsolved mysteries in science today. Some physicists even suggest the information is stored on the edge, like a 3D hologram. But one thing is certain. Long after the last stars have died, and long after the mighty quasars have gone dark, the universe will end with the quiet, final spark of the last evaporating black hole, returning all its energy back to the void. But don't worry, that dark, empty future is trillions of years away. We don't live in a dying universe. Right now, we are living in the absolute prime era of the cosmos, a vibrant, dynamic universe filled with colossal energy, and at the heart of it all are the active galactic nuclei, the ultimate masters of gravity and light. Whether you admire them safely from the side as a magnificent quasar, or stare directly into the blinding, terrifying beam of a blazar, it is all just a matter of perspective. One single, terrifying cosmic monster wearing two different faces. We are incredibly fortunate that our own local black hole is resting, and that these extreme cosmic beams are safely billions of light years away. That incredible distance allows us to safely study these titans, catching their ghost particles deep in the Antarctic ice and deciphering the most extreme laws of physics. Because when we look up at the night sky today, we are no longer just seeing quiet, peaceful stars. We are witnessing the ultimate, violent beauty of a living universe. The cosmos is far more complex, dangerous, and magnificent than we ever imagined, and we are just beginning to understand it. If you enjoyed this journey into the cosmic extremes, make sure to hit that like button to feed the YouTube algorithm and subscribe to the channel so you never miss a deep dive into the greatest mysteries of space and physics. Want to know what actually happens if you fall past the event horizon of a black hole? Click the video on your screen right now. Until next time, keep looking up and keep questioning the cosmos. See you in the next one.
Cosmic Master Plan to Act. Thank you for watching.